Okay. Sorry about that delayed start. I tried to get my screen up so I could show you the linear regression plot for the NVIDIA stock from last year. I'll try to get that running, or if I can't succeed between now and Thursday, I'll just post the file. Okay, so I'm going to take it a little easy between now and the last lecture. Not that the material I'm going to cover is unimportant, or in fact we're going to cover it on the final, but the pace is going to be slow. So let me just do a quick review of least squares estimation or approximation. In its general form, we had a subspace that was spanned by a bunch of vectors. I'm going to draw two here. And we wanted to find a best approximation to a vector B that didn't sit in that subspace. And we found that the best approximation is when we do a projection onto the subspace spanned by A1 and A2, so that this yellow vector here is our best approximation. And it had the property that the error vector, which is given by, what color is good here? Let's do orange. The error vector, which is B minus our best estimate, is orthogonal to the span of A1 and A2, which means it's orthogonal to A1 and orthogonal to A2. And if I have more vectors, if I have a set of n of these, then that error vector is orthogonal to A sub n. Here, each of the A vectors is in Rm. So I'm looking at solving the system of equations Ax equals b. This is m by n. This is n by 1, and this is m by 1. Because b doesn't sit in the column space of A, remember A is the matrix formed by putting all these columns together next to each other. So the span of A1 through AN is what? What do we call that? The what? I heard it. Column space of A. Okay? So our error vector is orthogonal to the column space of A, and it's orthogonal to each of the individual columns. Now, because we can't find an exact solution, we solve the following system. Solve. And the x hat that we found was, what was it? Does anybody remember? You want to tell your neighbor what that x hat was? If you ever forget, start with the equation Ax equals b. This is a thin and tall matrix. You want to turn this into a square matrix. What do I have to do to turn what's multiplying x on the left-hand side into a square matrix? Multiply by A transpose. So A transpose A times x is A transpose b. And then what? And what I get for x is what I call x hat, and that's what? Huh? This is square, right? If we make a certain assumption about this matrix, I can get rid of it on the left-hand side. What's that assumption I'm going to make? That it's invertible. If it's invertible, then what's x hat? A transpose A inverse A transpose B. And what does that make B hat? So actually, let's copy this here. A transpose A inverse A transpose B. And B hat is simply A times x hat, no? So I simply multiply whatever x hat is, pre-multiply it by A. And I have A times A transpose A inverse A transpose B. Now, this matrix I'm going to call PA. It's the matrix that projects any vector, arbitrary vector B, onto where? Into the column space of A. Question? Pardon me? Oh, move the podium up. Thank you. Sorry. So PA is the projection matrix that maps an arbitrary vector B onto the span of A1 through AN, and we know that that span is the column space of A. And this expression that we have for the projection matrix should remind you of the single vector case. When A was just a single vector, A, then PA was simply A transpose A inverse A transpose. So that's basically a summary of what we've done. Now, any questions up till now? Yeah. Yes, the accuracy is measured by this. Yeah, so in linear regression, you would have m measurements, right? You'd get an error vector, which would be the difference between what the data point is, what you've measured, and what the value of that straight line is that you've been sending through the data. So at every point, I'm going to get to that. I'll have a 3-point example that illustrates this. So you measure the error for each of those points, you square them, you square each of them, add them all up, and then you can divide by the number of measurements to get the value of the average error at every point. And you can compute percentage error from that. So if I'd been able to show you the NVIDIA stock, for example, it would have, I plotted it for, I think, 8 February 2016 to about, I think, sometime in November. And I had 202 points. 201 points. And it started at about $24 here and about $91 here. And near the end, it actually tailed upward. So when you do the linear regression, you'll get a line. So there are these data points that are actually the stock closing price. Okay, and you take the error at every point. And let's see, I turned off my computer, but I think the error was about the average error was about 20 cents per day. And even if you look at it at the lowest end, that's a pretty small error. That's 0.7% error. So this happens to be a stock that behaved very well according to a linear model. Not so near the tail end. So in fact, the last several days of that period that I picked had a disproportionately high influence on the mean squared error, because remember, we're squaring the error. So the more the distance is between what you measure and what the actual ideal line is, the greater the effect. Okay? But essentially that's this. I hope that gives you a qualitative answer, at least for your question. So you measure the distance between some points are above the line, some points are below the line. So the error for any particular day might be positive or negative, but we're squaring them. We're interested in the square. So you square each of those errors and then add them all up. So you get a total error squared. And then you divide by the number of, well, actually, you square it. You square each day and add them all up. You get the magnitude squared. Then you take the square root, which gives you the magnitude of the error vector, and you divide by m. And so for NVIDIA, it was something like 0.2 for the particular period that I plotted. This was the average error per day, which is pretty small. Okay. Now, one question that I tried to address near the end of the last lecture was, what is it about the A matrix that allows us to make a bold statement that A transpose A is invertible? I want to make sure that everybody's clear on that, because that's an important assumption that we're making. So, what I showed at the end of the last lecture was that the null space of A transpose A is the same as the null space of A. We showed this last time. Why is this important? Well, when is A transpose A invertible in terms of its null space? When its null space is only the 0 vector. So A transpose A is invertible if and only if the null space of A transpose A is only the 0 vector. But what we showed last time is that the null space of A transpose A is the same as the null space of A. So what does that say about the null space of A? A transpose A is invertible if and only if the null space of A is 0. Because these two are the same. Now, A is a tall matrix. It's m by n, and m is in general greater than n. It could be equal to n, but in general we make more measurements than necessary because we have measurement error. So what does that say when I look at A and its columns, and I say that the null space of A is only 0. What does that say about the columns of A? Linearly independent. So so basically we've reached the following conclusion. A transpose A is invertible if and only if A1 through AN are linearly independent. That's the result we want and the one we need. So as long as the measurements and your model are such that when you make all your measurements, you have linearly independent columns, you're good to go. You can actually perform a linear least squares estimation. The more measurements you make, in other words, the taller this matrix gets, the likelier it is that you have linearly independent columns. So even if up to here, let's say I've made 10 measurements, up to here, somehow these columns are linearly dependent. I make the next set of measurements, it's unlikely that it becomes less likely. The more components you add to each of these vectors, the less likely it is that they remain linearly dependent. So for most real-world conditions, as long as you satisfy this, you're in reasonable shape. And there are, of course, numerical ways of determining how close to singularity the matrix, any matrix is. But that's well outside the realm of this class. So for us, what's important is that as long as the A matrix has linearly independent columns, we can perform linear least squares estimation. So in other words, in the diagram that I drew there, for the case of just n equals 2, all we want is A1 and A2 to be linearly independent. And then I can project the vector B onto their subspace and figure out an estimate. Question?
Each row is a measurement?
Each row will correspond to a measurement. Yes, that's right. Okay. Let's do a toy example. So I grabbed this from one of the editions of Gil Strang's books. Linear regression example. It's essentially a miniature version of this one. So let me give it some context. Suppose you are interested in knowing the position of a vehicle. That moves along a straight line. Okay? So you know the vehicle starts at some initial position and is moving at a constant speed. What you don't know is what that initial position is and what the speed is. So there are two unknowns. So x0 is initial position. Of the vehicle, and x1 is its speed. I should say velocity because it could be negative. Velocity. You're assuming that the vehicle moves at a constant velocity. That's your assumption. That's your model. So your model is according to this equation. Okay? So these are unknowns. The vector x is unknown. What you do is make a bunch of measurements. So you just observe the vehicle from over a certain set of times. So measure position of vehicle at m time instants. Let's call them T1 through Tm. So what you have is a set of measurements like these. Okay? The problem is your measurements are faulty. So there's some error in your measurements. If I had perfect measurements, how many measurements would I need to make? 1? 2. I have 2 unknowns. If I make 2 measurements, if I measure the position of the vehicle at 2 time instants, that's all I need, because I need 2 points specify a line. Okay? The problem is I'm not making accurate measurements. I have erroneous measurements, faulty measurements. So I make more measurements than I need. So m greater than 2. Make more measurements. Let me put this here. M greater than 2. Make more measurements. Than unknowns. I have 2 unknowns, so I make more than 2 measurements. And then I try to find the best estimate. So the set of equations that I've set up here, can you talk to your neighbors and write this in terms of an AX equals B set of equations. What's the matrix A? Well, the vector X we already know, and what's the vector B? So fill in these blanks, please. Neil. What have you got for us? Oui. What's going on with this mic today? It's missing the sponge.
The first column of A will be all ones.
Loud.
The first column of A will be all ones.
All ones for the first column. X naught appears as X naught in every equation. So the first column is all ones. What's the second column?
T1 through
T1 through Tn. So X naught times 1 plus X1 times T1 equals Y of T1. Y of T2. All the way to Y of Tm. That's your set of equations. Okay? The problem is this B doesn't lie in the column space of A. So B doesn't lie in the column space of A because of noisy or, for some other reason, erroneous or faulty, whatever you want to call it, measurements. So this is actually equal to some magical B hat, which does lie in the column space of A, plus an error vector. And we're after that B hat that makes the error smallest in the sense of least squares. Is everybody with me so far in setting up the problem? I've got two unknowns. It's a linear model. It may turn out that once you do the analysis, the error is not acceptable. Maybe if you try a polynomial instead of a straight line, you get a better error in the end. Okay? So that's a separate problem. That's a model identification or system identification. And you'll see a lot of that actually in machine learning. So right now I've assumed that the model that governs this system is a linear model. And that's reasonable based on what I said. If your assumption about the velocity of the car is correct, or reasonably correct, namely that it's moving at a constant velocity, then this is a reasonable model. Okay. So now let's put in some numbers. So I'm going to just do the problem for, or I'm going to have you do the problem for m equals 3. Because this is a toy problem and we need something reasonable that we can work with in class. So my measurements are as follows. Let me write that here. First of all, my time instance given by T1, T2, T3 are 0, 1, and 2. So I'm measuring, oh, it's kind of silly because I'm measuring at the initial time, but remember our measurements are faulty. So these are my time instants, and the actual measurements I make, which are yt1, yt2, and yt3, which are y at 0, y at 1, and y at 2 seconds, are given by, what numbers did I have? -1, -3, and 1. This is where Strang's example kicks in. So it may not necessarily fit our car model. But whatever it is, it's a linear model, and these are the measurements we make. What I want you to do is find x hat, the best estimate. The best estimate for the initial position and the velocity. Go for it. So construct your A matrix for the particular numbers I gave, and do that. What's the size of A transpose A? A is what? 3 by 2. So A transpose A is what? Huh? 2 by 2. And you know how to invert 2 by 2 matrices. Okay, go for it. Talk to each other, people. Talk to each other. Okay. Neil, you get to pick the next person. You are?
Matt.
Matt. Go for it, Matt. A transpose is?
1, 1, 1, 0, 1, 2.
Uh-huh. And I multiply that by A. And what do I get?
3, 3.
So all ones times all ones gives me the sum of the entries, which is 3. And then the sum of these 3 is? 3. Here? 3. And then 5. 1 times 1 plus 2 times 2. That's 5. Okay? Notice A transpose A is symmetric, as you would expect. And what's the inverse, Matt? 3 times 3. And then?
And then you flip like A and B, so it should be 5, 3, negate
The other two negative. So the determinant is 15 minus 9, that's 6. And I have 5 minus 3 minus 3, 3. That's A transpose A inverse. What's A transpose B? A transpose you've already given me. And my B is what? Is that right? Yeah. So I need that, right?
Yeah, that should be -1, -3, and 1, so that should be -3.
-3, -1, -3, that's -4, plus 1. -3.
And then 0, -3, and 2, so that should be
-1. Okay, that's A transpose B. And so my X hat is A transpose A inverse A transpose B, which is 1/6, 5 minus 3 minus 3, 3 times minus 3 minus 1. And what does this give me, people? -2 and 1. So what does that say about my linear model? Y of t is -2 plus t. That's the equation of the motion that I found. That's the best fit linear model. Okay, now, so this is x0, and the 1 is x1. x0 and x1. That's what I found. Okay, now let's plot everything that we've been talking about. This is the time axis. I've got times 0, 1, and 2. And I've got values down to -3. So this is -1, -2, -3, 1, 2. This is y of t. And my measured values were what? At t equals 0, it's what? -1. So that's my first data point. That's what I measured at t equals 0. At t equals 1, I measured what? -3. So that's down here. And at 2, I measured 1. So that's up here. So I've got these three data points, and I'm trying to fit a straight line through them. Terrible, terrible. And, well, we got a solution. We got the best solution. We got minus 2 plus t. So, can you tell me how to draw that straight line? What's the vertical intercept? Negative 2, so that's here. And what's the horizontal intercept? 2. So these are the 2 points on my linear model, and I draw a straight line through them. This is the best fit line. Okay? Now, what are my errors? The error, look at what I wrote up there. The actual measurement is where the straight line goes through. So B hat is where the straight line goes through, plus some error. So the error here is the actual measurement minus the ideal model. The error here is the actual measurement minus the ideal model. And that. Okay? So the way I drew the arrows is that I know B is B hat plus the error. So the error is B minus B hat. So what's the error here in terms of magnitude? Epsilon 1. If I were to write this as a vector, epsilon 1, epsilon 2, epsilon 3, what would it be? What's this one? 1. What's this one? Negative 2. And this one? 1. 1, negative 2, 1. And you can figure out the magnitude squared of that vector and divide by the number of data points to get the average error. Okay, so magnitude squared would be 1 plus 4 plus 1. And the average error then would be 1 over the number of data points times the actual magnitude, which is square root of 6, whatever that number is. Okay? So our procedure guarantees that there is no other line you can plot through these 3 points that would give you an error as good as that. If this is bad, the rest are even worse. If it's too bad, if it's unacceptably high, then there's something wrong with your model, and you need to try some other model, maybe a parabolic model, a quadratic. Yeah?
This is assuming that error is the square error.
Yeah, so the whole process of least squares assumes that your optimality criterion, what you're trying to, your cost function, your objective, is the square of the error. Yeah. Any questions on this toy example? Obviously, if we make more measurements, you're going to have to go to Excel or MATLAB or Python and run those calculations. Yeah?
So what if after I run my least squares and I find out that the regression line I come up with is not physically sensible? How would I go about solving that problem?
So the question is, what happens if I do the regression model and I come up with something that's not physically sensible? Then there's something wrong with your model. You have to try a different model. So linear model here, if it ends up being not sensible, like I said, you may try a parabolic model, an exponential model, or a trigonometric model. You try a different model. So model selection is a related but separate problem. Yeah. I mean, a lot of machine learning has to do with that. You look at a real-world situation, you make measurements, and you got to figure out. In fact, on the electrical engineering side, historically, that's been called a system identification problem, and it's a whole body of research. What is the system that you're looking at? What's a good model for it? So finding that good model is one problem. Then among that class of models that you found, in this case, that would be a linear model, what's the best linear model that fits your data? So yeah, they're related, but they're separate problems. Okay. Now, let me see how I'm doing with time. Do you need a break? Go for it. Take a break. Yeah. Sorry, I can't hear. The bottom right here? That's the average error. So I have 3 measurements, so I divide by 3. And this let me rewrite this. Average error is 1 over m, the magnitude of E. So in our case, m is 3. Magnitude squared of E is 6, so the magnitude of E is root 6. I'm going to pull a stunt and define a new time axis, which is the old time axis minus 1. And I'm going to write the, so if I were to do that, what's the new model for the motion of the object? So if you look at the plot above, I am moving things to the right. So now I have tau. So at let me make sure I got the sign right. So y at tau equals 0, I want to be y at t equals 1. Y at tau equals minus 1 will then be y at t equals 0. And y at tau equals 1 would then be y at t equals let's see, tau equals, no? Yeah, tau, I want to center this. So y at tau equals 0, I want to be y at t equals 1. Y at tau equals 1, I want to be y at t equals 2. That's what I want. If these are if I redefine my time axis in this way, can you tell me what my new A matrix is? My new B vector is what? Does that change? This is y at tau equals minus 1, y at tau equals 0, and y at tau equals 1. What's this vector? Minus 1. What was it? Minus 3 and 1. What is my new vector? A. Does the column change? And what are my new times? 1, 1, 1, negative 1, 0, and 1. What's special about the columns of this matrix? Why did I do that? They're orthogonal. By a simple translation of the time axis, I have made the columns of the A matrix orthogonal. So this is a new A matrix. It's not the same A matrix as before, but I don't want to keep putting tildes and hats on things. So now my system of equations is, so basically I have taken my time axis, my reference time, and shifted it to the middle point. This number 1 here, I didn't just pull out of a hat. It's actually the average time, which is T1 plus T2 plus T3 divided by 3. It's the average of the old times where I made the measurements. And the old time measurements were done at 0, 1, and 2. Oh, wait a minute. Yeah, so 0 plus 1 plus 2 is 3 divided by 3 is 1. So I've translated the time axis by 1 point, and by doing that, now I have a system of equations where my AX equals B is 1, 1, 1, minus 1, 0, 1. X equals, what is it? Minus 1, minus 3, and 1. This I may have to change to a new variable, so I'm just going to put a tilde over it. Because my new equation is different. It has a different set of parameters. Now, what's special about this A? When I do A transpose A, what do I get? What kind of a matrix do I get? Diagonal. Is it easier for you to invert a diagonal matrix? Mm-hmm. So, can you compute this matrix? Question? So the old times were 0, 1, 2, right? And when I look at the first column of A, and I take the dot product with the second column, I don't get 0, do I? Because they're not orthogonal, right? But when I subtract just the right amount from these and center my time axis so that the time instances are symmetrically situated around 0, then when I take the dot product of this vector with that vector, I get 0. I guess what can probably help you more is to keep in mind that when you take the dot product of the all ones vector with any vector, call it V, you are doing what? V1 through Vm, right? What does that give you? The sum of the entries. So anytime you take the dot product of the all ones vector with some arbitrary vector, you are taking the sum of the values of the vector. What I want is to create a second column whose entries sum to 0, which means they're orthogonal to the all ones vector. And the way I do that is take the 0, 1, 2, whatever time instances I have. They don't have to be 0, 1, 2. They can be any arbitrary set of T1 through Tm. If I subtract the average, then I'm guaranteed that when I sum the new values, I will get 0. So my goal is to orthogonalize the columns of A, which makes my subsequent calculations easier. If the subspace onto which I'm projecting, here's the ultimate goal. So if the subspace onto which I'm projecting, so this is my B vector, and I have A1 and I have A2. If A1 and A2 are already orthogonal, I can figure out the components of B hat by projecting B independently into A1 and A2. Let me just point that out to you. Actually, it's a good question. It motivates. So let's say I have I'm looking for a B hat, which is alpha 1 A1 plus alpha 2 A2. I'm looking for some A hat, which is a linear combination of these two. If A1 is orthogonal to A2, then I can find each of these coefficients independently of the other. And the way that works is that I simply, to find alpha 1, I simply project B onto A1. So this is B hat. This is alpha 1 A1 plus alpha 2 A2, comma, A1. And based on what you know about inner products, how can you expand the right-hand side? What's your name? Lace. A1 plus? Yeah, but we want to get there. Alpha 2, A2, comma, A1. And because A1 and A2 are orthogonal, what do you know about the second term? It goes to 0. So you can figure out alpha 1 by simply dividing the projection of B hat onto A1 and dividing it by the magnitude squared of A1. What do you think alpha 2 will be? Instead of A1, you have A2. Orthogonality is really cool. You want stuff to be orthogonal. Except perhaps in love and marriage. I guess it could be worse than orthogonal. It could be pi out of face. So orthogonality is great. And also in the translated into our linearly squares setting, it means that my A transpose A is diagonal. And diagonal matrices are much easier to invert and deal with than full matrices. So I hope this gives you a sense of why orthogonality is good. If A1 and A2 were not orthogonal, then I couldn't use this process to find alpha 1 and alpha 2 easily, because the second term won't disappear. And when I try to find alpha 2, when I project B onto A2, the first term won't disappear. So how do we do this orthogonalization? So how do we take, so this is our question then. How do we take linear, and I'm going to do this for 2 vectors, and we can expand it to more than 2 vectors later. Linearly independent vectors, A1 and A2, and create orthogonal vectors out of them. Let's call them Z1 and Z2 out of them. The answer is through a process called the Gram-Schmidt orthogonalization process. And you know everything there is to know about this process because you know how projections work. If you know how projections work, you should have absolutely no trouble understanding how Gram-Schmidt works. So let's set that up. Let me get my notes here. Okay, so I've got A1, A2, linearly independent, but not orthogonal. So here's my A1, and here's my A2. Okay? They're not orthogonal, but they're linearly independent. The Gram-Schmidt process begins with one of these vectors. So I'm just going to, without loss of generality, start with A1. I'm going to define as my first vector A1. Okay? So I'm just going to let this be z1. What I'm after now is a second vector z2 that is orthogonal to z1 and together with z1 spans the same subspace as a1 and a2. So we want a z2 that has two properties. First of all, we want z2 to be orthogonal to z1. And we want the span of z1 and z2 to be the same as the span of a1 and a2. Right? Otherwise, there's no point. We want to stay in the same subspace. So if you think about R2, for example, I might have a vector a1 in this direction. Let's say that's 1, 0. Doesn't have to be unit length, but let's say it is. And my a2 might be 1, 1. Do you agree that these two vectors in R2 span R2? Okay, so the subspace I'm living in happens to be R2, not some subset of it. And what I'm after is an orthogonal vector to A1. What's a good choice? 0, 1. Oh, wrong color. So this would be a good choice for Z2. What if I had started with A2 as my first vector? 1, negative 1 that would then be the orthogonal one. So your choice of which one you start off with does make a difference, but you still stay within the same subspace. It doesn't matter which one you start off with. Whatever I label with the subscript 1, I'm just going to start off with that. Okay, question there? I saw a hand raise. Okay, cool. So now, you remember from the projection story that if you were to project A2 onto A1, you'd get some best estimate, but I'm not concerned with that best estimate right now. I'm concerned with this orthogonality. And this vector, which we used to call the error vector, will it work as my Z2? Yep. So what I used to call the error vector is now my Z2. This vector, whatever you want to call it, A2 hat, was obtained from A2 by doing what to A2? A2 hat. What did I do to A2 to get A2 hat? Project it by multiplying it by some projection matrix, P1. This is the orthogonal projection onto the span of A1, which is the same as the span of Z1. Because A1 and Z1 are the same. What do you think Z2 is? Isn't Z2 simply A2 minus A2 hat? Isn't Z2 A2 minus A2 hat? In other words, if you look at A2, I can write it as the sum of A2 hat and Z2, no? This orange plus green gives me A2. So green is what? A2 minus A2 hat. But I know A2 hat is P1 A2. Isn't this simply I, the identity minus P1, A2? Do you agree that these two are equal? Identity times A2 is A2 minus P1 times A2, which is A2 hat. That's my Z2. So anytime you have an orthogonal projection onto a subspace, there is a complementary orthogonal projection that takes you to the orthogonal complement of that subspace. And that projection is given by the identity minus whatever projection you used. So let me go here. So Z1 equals A1. Z2 is I minus P1 times A2. I minus P1 is the projection. So P1 takes A2 and shines it this way. I minus P2, it's as if the sun is sitting here and shining horizontally, and gives me the shadow along the orthogonal complement of A1, which is in this direction. Okay, so P1, sun shines downward. I minus P1, sun shines this way. And these two are orthogonal to each other. Any questions before I say anything more? Is the picture clear? Yeah. I am going to use the projection formula.
So why use the P1?
Because it's compact. I don't have to put in the gory details yet.
Yeah, but isn't the point of doing this is to make this calculation easier?
Yeah.
But we're using this to express that.
No, what I'm doing is I'm describing the geometry of a situation where I start off with two vectors that are not orthogonal. I'm trying to find a compact way of expressing, of going from these two non-orthogonal but linearly independent vectors to a pair of orthogonal vectors. And that picture is coming from my projection story. So all this stuff about linear regression is one application of what I'm about to say here. Yeah. Okay, so now what is P1? Can somebody tell me? This is A2 minus, what's P1? What's the matrix that projects onto the direction Z1? Z1. Z1 transpose. Z1 inverse times Z1 transpose. Huh? So this is just the magnitude of Z1 squared. That's in the denominator. Am I out of time?
Yeah.
Oh! Okay, I'll be done in a moment. So this is now Z1. And I have a Z1 transpose times A2. So I can write A2 as I solve for A2. It's Z2 plus Z1 transpose A2 over Z1 magnitude squared Z1. Do you agree? I just took this to the other side and expressed A2 in terms of what's on the other side. I think I better stop here before I tick people off. So I'm going to continue on that on Thursday.